Hello everybody on this beautiful Saturday afternoon or evening already, evening. So now we are continuing with the next paper from my own research regarding the hydration processes. Yeah, I showed you in the former video that the water in the Earth's mantle is not like as thought before, mainly on hydrous minerals. It is or in nominally anhydrous minerals, because for hydrous minerals like amphiboles and biotides, the pressure and temperature conditions, especially the temperature conditions in the Earth's mantle, are too hot. So, and therefore, since about 20 years, a lot of scientists, including myself, working on this to figure out where is the water now in the Earth's mantle. So, and before I have shown you from a publication which I have published in 2008, that this water is sitting on point defect and planar defect structures in the water-free mineral, like in olivine. So, but now on this publication, which I have written in 2009 and published in 2010, I made just theoretical calculations, yeah, if it is possible to store the water there, and if it is possible and fits together with the geotectonic setting which we found in the Western United States. So, and therefore this paper is entitled Hydrating Laterally Extensive Region of Continental Lithosphere by Flat Subduction, a pilot study from the North American Cordillera. So flat subduction, yeah, that is also something which is very new in modern geoscience, because in former days people were always talking about subduction, but we can have a flat subduction and we can have a steep subduction. So, and between a flat subduction and between a steep subduction, there are significant differences, yeah? So, and that I will show you then in this example, and I will show you the calculation what I have done here. And I have carried out also a geophysical survey to figure out how the S-wave velocity, or more, or let us say better, how the S-wave velocity anomaly is changing, yeah? And I will show you there some other pictures, yeah? So, now we are starting here with this paper, and I will send you the paper then also around as a PDF. At first we are starting here with this topographic map which I have constructed here. You know, you can just make such maps using, for example, GeoMap app. You can just download it from the internet, it's for free. And then you can see here some nice features. So you have here, I mean, the continent of North America, and the topography that is actually from the Western United States. So, and then you can see three significant things. So here very close, I mean on the western side here, the rocks are strongly deformed, yeah? So, and then I have separated the western side from the eastern side, and here on the eastern side your rocks are not deformed at all. That is all flat. So, and here it is strong deformed, and it is strong deformed because we have here a collision zone, yeah? And the collision zone is caused by the eastward dipping subduction from the North Pacific plate. So, and therefore these rocks are, or rock units are above deformed. So, and these rock units here are very old, yeah, they are 2.0 to 2.6 Ga in age. That means 2.6 Ga, that is Archean, yeah, and 2.0, that is Paleoproterozoic, yeah. So, and then we have here the location where I have sampled the rocks, yeah. That is the Sump volcano in the Colorado Plateau. And the Sump volcano is called the Sump because it looks like a thumb, yeah. So, and then when we are looking, I have here in this yellowish circle, I have put an outline here from the Colorado Plateau, and the Colorado Plateau is undeformed here compared to the strongly deformed surrounding areas, yeah. So, and behind it is again deformed. So, and therefore it is something very unusual, but you can find this on different spots on Earth. You can find it also, you know, in the Tanzania craton. Yeah, the Tanzania craton is an Archean craton. It pops up also as a very undeformed island in the strongly deformed surroundings. Yeah. So, and if it is here deformed to the west of the Colorado Plateau and to the east of the Colorado Plateau, there must be a third component controlling it from beneath to come up with a reason that these rock units are not deformed, yeah? So, because, I mean, here we have the same rock types with the same age as here in the surroundings, yeah? So why it is then here not deformed and here it's strongly deformed, yeah? So because regarding to the plate tectonic, the theory of plate tectonic from Alfred Kröner, no, Alfred, what's his name? Not Alfred Kröner, that was my PhD supervisor, but he was also very famous. And the plate tectonic was developed by Alfred, that is now painful. What was his name? Alfred Wegener. Wegener was his name. Sorry that I could forget this. Yeah, that was Alfred Wegener. And Alfred Wegener was the first guy who described plate tectonic processes, but he described it only in a two-dimensional way, yeah? But if we are looking at our planet, then we are dealing with three dimensions. So, in the third dimension comes from the upper and from the lower mantle beneath, yeah, of course. Because here we have the subduction zone from the North Pacific plate beneath the North American continent. So, and then you can see or you can estimate here just by using such a GIS software how far the subduction goes. Yeah, that is just there where you have everywhere your strongly deformed rocks. And here it stops very abruptly, and to the eastern side everything is flat. Yeah. So far to this. So, and then I have constructed, using literature data, such a flat subduction model, yeah? Such a flat dipping subduction does not have a mantle wedge between the subcontinental lithosphere and the dipping slab, yeah? So, I mean, normally when you have a steep dipping subduction, you have a mantle wedge. The mantle wedge is here totally missing. So, and why do we have yeah, a flat subduction, yeah? Flat subduction occurs when your subducting slab is too buoyant, yeah? So, and what makes them buoyant? That is the weight. So, and therefore, if you have a highly hydrated slabs, if you have a very highly hydrated slab, that huge areas are serpentinized, then you are not subducting at all or only a part of it, then you are forming an ophiolite. Yeah, we have done this in the mineralogy class, we have discussed this, and we have discussed this also in the fourth year class. Yeah. So, If your dipping slab is young and only partly hydrated, then your slab has also is also less in weight, and therefore it has a lower density, and then it will not dip immediately down. It will just bump up just directly beneath the continental lithosphere. Yeah. So, and then we do not have a mantle wedge. So, and if you don't have a mantle wedge, then your subduction zone is much cooler. Why is this? Because if you have a mantle wedge, then your dipping slab becomes warmed up from both sides, from beneath and from the mantle wedge above. Yeah. So if this mantle wedge is missing, then the slab becomes not heated up from the upper part, it becomes only heated up from below. So, and therefore, when the temperature's low enough, then you will not form melt. No, then your hydration will take place. Yeah. So, and this you can just do this by using simple mathematical and phase petrological calculations to calculate if at this certain depth and these temperature conditions, if you have or if your hydrous minerals are stable. Yeah, that is this. Yeah, if they are stable under this pressure and temperature conditions. And you know that the mineral antigorite, that is the serpentine, can be stable at very high pressures and will dehydrate at 600 degrees Celsius. Yeah? So, and this you can just easily calculate. So, and to calculate this, you don't need a lot of money. You can just use a bulk rock chemical analysis. I mean, I have used my own bulk rock chemical analysis, but you can also just check the internet on certain and using certain databases, and then you can calculate. And the software for the calculation you can also download for free from the internet, if you know how to handle this software. Or you can do just all these calculations by yourself, by hand, which is very, very time consuming and very, very difficult. So, but you should know how to do this. Therefore, I will do this with you in both classes, only a small introduction, that you get an idea for what this is necessary to learn thermodynamic or mineralogical thermodynamic and phase petrology, which we will continue then in chapter 9 of the mineralogy class and in the practical of the 4th year class. And we just using easy relationships like the CMS system or the MSH system. Yes, that's it. So, okay, then you can calculate all the conditions from your bulk rock chemistry which you are using, yeah, at a certain temperature and then a certain pressure. So then you are calculating which minerals are stable at 533 Kelvin. You must then add the 273 to get then the temperature degree in Celsius, and here we have the pressure. Then you know these and these minerals are stable. You have to subtract the 273, yeah? Then you know these and these minerals are stable, and that and this and that is then the regarding bulk rock chemistry. And here you have then the density of the rocks. You can all calculate this theoretically. You can calculate the theoretical p-wave velocity. You can calculate the theoretical s-wave velocity, and you will get this results here in kilometers per second. So then I did it for 593 Kelvin and 20,000 bars, then you are getting then the first olivine, yeah, and then at 653 and 30,000 bars, and then you are getting always the change in your bulk rock chemistry and the change in your density of the rock sample, and you change on the P wave velocity and then the S wave velocity. So, but you can calculate this for a lot of different things. The starting point is you must just use one analyzed bulk rock composition there, and therefore you can just go there, select an xenolite, such as lersolite, make a powder, and then you can analyze with XRF the bulk rock chemistry at this pressure and temperature conditions when your rock has equilibrated, yeah? So, and that is then probably here. Yes, we have then 1073 degree Kelvin, that is 800 degrees Celsius, and 60,000 bars, yeah? And then we have a garnet lersolite, OPX, CPX, olivine garnet, and then you have here all the density is much higher compared to the beginning. The P wave velocity is faster, and the S wave velocity is also faster, and this is all values which you can calculate using just thermodynamic databases. Yeah, there are books are available, and there is everything written inside what you need for your calculations. So, but now you are calculating this, and I use there the CF-MASH system, yeah. For the fourth year students, you know by now the CF-MASH system, that is calcium, iron, magnesium, aluminium, silica, water. So, and for the third year students, we have dealt by now with the MSH system and the CMS system, yeah, and that is for you enough. But for you, I like to show you what application is behind for that, what you have by now learned in class. So, and then you can calculate such a PT pseudo section, and we will do this in both classes. In the practicals, we will just not calculate such a complicated PT pseudo section, because then you will it will take too long. We will just calculate one curve or two curves, that you know how in generally does it work, what the role spills the Gibbs free energy, what is the role of the enthalpy, what is the role of the internal energy, and what is the role of the entropy, and all these parameters which I will now introduce on the Mineralogy 9 class, and I have already started to introduce it. So then we have the picture number B. I mean in A we have then all the different phase fields, yeah, for the given bulk rock chemical analysis which I have analyzed, yeah, and then I have calculated this pseudo section with these different phase fields, and then we have, I put in this PT path from A to A, B, C, D, E, F, G here in yellow. So then the next question is, from where do I have this PT path? I just have taken this PT path from this publication, yeah. So, and then I used always the pressure and the temperature conditions in our depth-related model, yeah. So, and then we have here along this, we can then construct an PT path, yeah. So, and then at all these points, A, B, C, D, E, F, along the PT path, we have then following conditions, like I have written it here in this table. So, and then we have here this, and there I have these points, and then I plotted in this PT path 60 at a depth of 60 kilobars, that is then 180 kilometer, yeah. It goes down to 180 kilometer. Let us check here on this picture if this fits. and that fits, yeah, that is then in a depth here of about 180 kilometer. And then you have your PT path, and then you can describe what happens along your PT path, yeah? And then you can get an idea if it is possible to hydrate laterally such a huge reason by a subduction, if it is theoretically possible, yeah? It can also be that it is theoretically just not possible, yeah? And therefore you have to come from different sides from your research. You coming from the analytic side, I mean at first you have to go to the field and see it, yeah? Then you can make such a GIS map as I have shown you before, then you see, hoppla, on the western side it's highly deformed, on the eastern side not, there must be something, yeah? So, and then you going there to this volcano, sampling such a xenolite, doing such a bulk rock analysis. If you do not have the money now to fly to America, or you cannot go to America because of the virus, then you can just go to the library and checking for lersolite analysis, bulk rock analysis from this and that volcano, and then you have it as well. And then you can do such calculations. Having this pseudo section then calculated, which is very time consuming, then you can calculate all the different parameters. Here, for example, in the section B, how the density changes from point A to G. So, I mean, at first we have here very hydrous mineral assemblages, yeah. Here we have chloride, CPX, antigorite, brucite, yeah, brucite, MgOH. So, and here we have chloride, CPX, olivine, garnet, A-phase, antigorite. So, and here we have still the brucite inside. Brucite is then going out here along this curve. So, and here you have then the antigorite and the A-phase, yeah. Up to this point you have still hydrous phases, and here you have still the antigorite, because here you have the dehydration curve of the antigorite, and finally the antigorite disappears at this point, but then you have still, as a water carrier into depth, you have still the A phase, which is a modified antigorite. So, and during hydration here along your PT path, your rock becoming more and more dehydrated, and you are forming mineral assemblages with anhydrous mineral assemblages, and these mineral assemblages having then a higher density, yeah? So then your rock sample will become more and more dehydrated, starting here with density of 2.8 for a centimeter per cubic, for a gram per cubic centimeter. Here I have done it for kilogram per cubic meter, because I mean we are subducting a huge mass, yeah. So, and it goes up here up to a density of 3.5, yeah. There is quite a density contrast. So, and the next thing is, I mean, all these dehydration reactions, these are possible trigger for earthquakes, yeah, that is the next thing. So, and then I have calculated here the theoretical P waves along this path, yeah. From A to G, we are starting here with a P wave velocity of 6, yeah, and ending up with a P wave velocity maybe of 8.2, yeah. So, and here the same for the S wave velocities along the path. We are starting here at 3, ending up, let us say, at 4.7, yeah. These are theoretical values for a dry rock, yeah, because the computer program does not know if you are dealing with a dry lersolite or a hydrated one, yeah. That does the computer program not know. So, and then therefore we have also a change in volume, yeah. So we have here 3.8 joule per bar, and here we have just 2.8. So the volume becomes smaller because the density becomes higher. So, and here then the water concentration, I mean, if you are going here to the beginning, we have more than 10% water bounded in the rock, yeah? And here it starts then to dehydrate, and finally the water goes away, and this water will then also form melt, yeah, of course. So, and here you have then your anhydrous rock assemblage consisting of orthopyroxene, olivine, clinopyroxene, and garnet, yeah? So, and here I have then the stability fields done for the antigorite, for example. So here we have now the weight percent of antigorite in your rock. So at the beginning, your rock was very hydrous, yeah? We have 60 weight% of antigorite. More than 68%. So, and then it starts to, the antigorite starts then to more and dehydrate. Here we have only 40% of antigorite inside. Here we have 30%, and here the antigorite disappears then, yeah? So a lot of dehydration reactions will take place. Here the same for the brucite. At the beginning we have maybe 10% brucite inside, and then here it will then dehydrate at point number E. Same for chloride. We have at the beginning about 14% chloride, and here at point F it will then disappear. Here we have then even more chloride inside. We have 16% here, and here we have even 18%. So, and that is the small field of the A phase. We got only a little bit A phase inside your rock, inside the investigated rocks, because our PT pass is not, the pressure in our PT pass is not high enough. So, and these are just theoretical calculations which you can do. Totally easy, but you need a lot of knowledge and experience to do that. So, and then I have the next funny thing. I got from a colleague of mine, she is a geophysics. I got all this data about the S-wave velocities, what she has measured with her seismographs along the whole North American continent. Yeah, and here we have the shape of the North American continent, and in the white circle that represents then the Colorado Plateau, and the white dot, that is the location of the Samvolcano where I have taken the sample. So, and here we have the S-wave velocity anomaly in meters per second. Yeah. So, and what means anomaly? So we have the theoretical values for a lersolite, and these values we have also calculated, yeah, in these calculations which I showed you before. So, and here I have put in the S-wave, I have analyzed the S-wave velocity anomalies. I mean, the S-wave velocities, not the anomalies, the actual velocities, they are analyzed in kilometers per second. So, in the S-wave velocities are measured in meters per second. Yeah, that makes not such a big difference. So, and you are getting S-wave velocity anomalies. You can have them for either for two reasons. If you have melt sheets there, if you have melt sheets, then you will get negative S-wave velocity anomalies. So, or if you have hydrated components there, then you will also get S-wave velocity, negative S-wave velocity anomalies. Yeah. So, but now from the picture from before, from the subduction zone, we are too cold to form melt sheets there. So, and therefore we are looking now for if it is possible, or if we have S-wave velocity anomalies, and if we can observe S-wave velocity anomalies, then that is a proof for the laterally hydration of the lithosphere beneath the western United States. So here along Moho depth, and you know Moho depth, that is in a depth of about 33 kilometers in average, we do not have any S-wave velocity anomalies. We have here the dark blue, and we are here it's even a little bit faster. We have a little bit faster, that means, but it's still very low, it's 40 meter per second faster. That means there we have not hydrated anything. In the crust, in the crust, continental crust. So, but now we are going down to a depth of 70 kilometers, and there we can see that below the thumb, we have this orange color, and we have a negative S-wave velocity anomaly of about minus 300 meters per second. So, and it is cold enough that we cannot have or produce melt sheets. Therefore, hydration takes place. Or they can also talk about, meanwhile, from a wet spot instead of a hot spot, and people using this. So going down to a depth of 90 kilometers, we have still this dark orange field, minus 400 meters per second, minus 400 meters per second. There we are sitting in a depth of 90 kilometers, that is in the upper part of your dipping mantle slab, and there we have a lot of hydrous phases now, stable because it is not that hot. Going down to a depth of 150 kilometers, then we have here yellowish, and the S-wave velocity anomaly is nearly gone, because there we are not longer sitting at the top of our dipping mantle slab. We are sitting at the bottom of our dipping mantle slab, and there it is cold. So, and the proof or the implications from this manuscript is that we have theoretically proven that it is possible to host, or it is possible that we hydrate the continental lithosphere, or the subcontinental lithosphere laterally in the western United States. So that is now the theoretical proof. Before, in the publication before, I have shown you that we can host in these rock types water in nominally anhydrous minerals on point effects and grain boundaries. Now here you have the theoretical proof that it is possible, and in the next publication which I have written about this stuff, I will show you more measurements of the hydration and also the measurements of the mineral chemical composition in thin section. So, and then we have proven it completely. So, and that I will now record as next and load it up to you as well. And then you have to do something tomorrow because the church is closed.